morning. Let us do one problem. Let us solve one problem. So I say tutorial 2, and we like to see whatever we have understood, can we apply this for solving simple problems or not. Okay. What we have understood? We have understood one thing, dCm by d alpha, which is static stability parameter, and another is Cm naught. So let me create a problem. This is Cm, and let's see, this is Cl, and let us see. Let us frame a problem that we want to fly an airplane such that the lift coefficient, or CL, equal to 0.6. Where from we get the CL 0.6? After all, what is this point? This point is cruise, that is our equilibrium. So lift equal to weight, lift equal to weight. So I know half rho v square SCL equal to weight, or CL equal to 2W by S rho v square. So suppose I am designing an airplane whose wing loading we have decided. We have decided what is the cruise speed, and we have decided what is the altitude at which I will be cruising. So if I put those numbers here, I get a value CL. And that value CL, let's say, for all those geometric parameters, that value is 0.6. Correct? So if I try to visualize, that means at this point, lift and weight are equal, and of course, since it's a cruise, thrust and drag are also equal. Right? And it goes without saying, the Cm is also 0, like this. Okay? Now the question is, what should be the value of, Cm naught if stability margin or static stability margin is 10%. This is the question. What is the question? What should be the value of Cm naught if stability margin is 10%? And I am going to fly at CL equal to 0.6. The moment I mention stability margin, it should come to your mind that dCm by dCl is nothing but minus static margin. You know, we have developed this relationship with some approximation, but we will carry on with this. So what is dCm by dCl? So dCm by dCl is minus 0.1, because 10%. 10% means what? It is actually, it tells you, what is this meaning of 10%? That means if this is the neutral point and if this is the CG location, then this distance is 10% of mean aerodynamic chord, MSE. Okay? So I know dCm by dCl is minus 0.1. So I know the slope, which is here. Since linear, it is same here and here, minus 0.1. So what is the Cm naught then? The Cm naught, you could see easily, it is 0.1 into 0.6, and that is 0.06. So I need Cm naught equal to 0.06. So when I am designing an airplane, I should ensure that Cm naught of aircraft, this is equal to Cm naught wing plus Cm naught fuselage plus Cm naught tail. What do you understand? The Cm naught 0.06 means the contribution from wing, contribution from fuselage, contribution from tail, when they add up, they should add up to 0.06. Suppose these two contribution is not giving me 0.06. If it gives 0.06, fine, plus 0.06, which is very difficult, you understand. Mostly we use cambered aerofoil, and the Cm naught fuselage is mostly negative, although small. So what is the option? Suppose let us say this total is giving us 0.01. Let us say this. Then remaining 0.05 has to come from tail. And how do we get the CM0 from tail? You know, for that we give tail setting angle. You can use those formula and find out what is the tail setting angle required for making this whole CM0 to be 0.06. The catch point is here. Right. Now let us further look into this problem. Let's say this is 0.6, this is 0.06, and let's say this is for xCg is equal to 0.3. xCg bar means xCg location non-dimensionalized with mini aerodynamic chord. Now if I move this Cg backward, let's say Cg is here, 0.3. Now I am moving the Cg backward. So what will happen? As I move the Cg backward, then the slope will go on reducing, and a time will come when this slope will be parallel to the x-axis, and that Cg location you all know is called neutral point. So what is the definition of neutral point? Is that Cg location at which dCm by dCl is 0, right? Other aircraft is neutrally stable in static sense. Now, if I am given this plot, xCg as well as the CL and CM0, if I try to find out what is the value of N0, I can easily find out. You could see that for, let's say, this combination, this is given. What do we know? We know dCm by dCl is minus 0.1, and also we know dCm by dCl is minus static margin, which is minus of N0 minus xCg bar. And you know dCm by dCl is how much? dCm by dCl is, the static margin is 10% we have mentioned here. So dCm by dCl is minus 0.1. So what I can write? I can simply write minus 0.1 is equal to minus N0 minus xCg bar, N0 bar. And so N0 bar will be equal to 0.1 plus xCg. xCg is given 0.3. So your N0 bar or neutral point is 0.4. So simple. So if a variation is given like this, Cm versus Cl, xCg is given here, and these values are given here, you can easily find out what is the neutral point of the airplane, right? This is one of the simplest things which you are supposed to do, in a sense that automatically it should come to your mind when you see such variations. Now let us try to be a little more creative. Let's say you have got N0 equal to 0.4 as given in the example. But you want that your airplane should have N0 equal to 0.5. That is what is required. I'm talking about design iteration, right? What is to be done? So again, revisit this graph. We say Cm versus Cl. This is xCg equal to 0.3, and this is 0.6, and this is 0.06. Most of the students, they start thinking, if I change the Cg, I will change the N0. But do you think it is correct? Answer is no, because Cg has nothing to do with N0. N0 is decided by whom? The neutral point is decided by whom? By the tail size, its aspect ratio, its location, by wing. its size, aerodynamic properties, fuselage, all the aerodynamic properties. So once the configuration is fixed, N naught is fixed, right? So by changing CG, you cannot change N naught. You can change the stability margin. That is different issue. But our problem is we want to change N naught. So what is to be done? So the best way to do is, if this is the airplane, this is the tail, this is the wing. If I want to change N naught from 0.4 to 0.5 or whatever number it is, the best way to deal this is you change the tail volume ratio. Tail volume ratio. That is, you remember, that is VH. Which was VH? VH was ST LT by S C bar. What is happening philosophically? Please see this. I want to change N naught from 0.4 to 0.5. So what I will do, I will either increase the tail size. Increasing tail size means drag also will increase, right? So it is better you take this tail little back. If you take it further back, then the slenderness of the whole airplane or length may increase. You may not like it. So either you increase a little bit of area, a little bit of length, or in effect, changing the VH tail volume ratio, this will immediately change the N naught value. So you can find out what is the corresponding change in VH required to make it from 0.4 to 0.5. So best way to handle is change the tail volume ratio. Okay, that you should not forget. Okay. Now, once this is done, let's also see another problem so that we can understand all these concepts very clearly. Let us see. Let this is 0.6, let this be 0.06. We are flying at this CL. Now, there could be a requirement that you fly at the same altitude but at a higher CL. The CL2, let's say this is equal to 0.8. So what will happen? The moment you try to fly at 0.8, the aircraft will generate a negative pitching moment. Right? But you want to trim this airplane at this CL without changing the stability, because all CG, everything remains same. So if you want to really do this, that means at this point, this negative pitching moment has to be nullified. So who will nullify this? We nullify this through by putting the elevator up. Because elevator up means it gives force like this, a moment our CG nose up. So I should be able to give that much of elevator which will neutralize this negative pitching moment at CL2, which is equal to 0.8. And how do I do that? We all know we use this relationship delta E equal to delta E naught plus d delta E by dCL trim into CL trim, and where this is minus Cm naught by Cm delta E plus minus dCm by dCl by Cm delta E into CL trim. And you could see easily that for an aircraft, the Cm naught will be available, Cm naught is available, Cm delta is the elevator control power, this is also available. Otherwise, you can also find out using its formula, Cm delta equal to minus VH neta t CL alpha tail, etc., and tau, etc., which you can check your notes. dCm by dCl, let's say 10% as given here, and CL trim is now it becomes 0.8. So simple, right? It reminds me of another problem we should also now discuss. Suppose an aircraft is cruising such that V cruise is 100 meter per second, rho is 1 kg per meter cube, that is that altitude where density of air is 1 kg per meter cube. Let's say S is 20 meters square, W is 2000 kg, right? And Cm naught is 0.06, Cm delta E is minus 1.0, and static margin is 10%. What is the elevator required if this question is asked? What is the elevator required? How do I do that? Again, I come back to that relationship delta E equal to delta E naught plus d delta E by dCl trim into Cl trim. Okay? What is Cl trim? Cl trim will be 2 W by S by rho V square. So I can always put 2 into W is 2000. Please understand, if you put 2000, this will be wrong. We have to put in Newton. So I have to multiply by 9.8. 2W by rho is 1, V square is 100, square into S is 20. So that will give me Cl trim. Delta E naught I will find out by minus Cm naught by Cm delta E. So values are given, minus 0.06 by minus 1.0. Then d delta E by dCl trim is minus dCm by dCl by Cm delta E. Again you know this, minus 0.1 divided by minus 1.0. So you will get d delta E by dCl trim, and Cl trim you have found from here. Plug in here and get the answer. They are simple as that. Okay? Now let us take another form of problem. Suppose we conducted a wind tunnel test and we observed this. Through a wind tunnel test, we found that Cm at delta E equal to 0 is 0.04 and Cm at delta E equal to minus 5 degree is 0.08. Right? So we are conducting a wind tunnel test. We have put a model, right? And this is the elevator here. One test we conducted where delta is 0. That time we measured Cm through strain gauge balances and we found it is 0.04. And second case, we put the elevator like this up, minus 5 degree, and then we measured Cm. That came out to be 0.08. Now the question comes, what is the value of Cm delta E how will you find out? That is the question. What is happening here, you see? This is 1, delta E equal to minus 4 or delta E equal to 0 degree, and this value is 0.04. Second case, delta E equal to minus 5 degree, and this value from here it is 0.08. Okay, so what is the value of Cm delta E that is being asked? What is Cm delta E by definition? It is delta Cm by delta delta E. So you could see, if I take this, delta Cm will be 0.04 minus 0.08 divided by 0 minus 5. please be careful about the sign, and that will give you the value minus 0.04 by plus 5 per radian. It will give this much of value per degree, not per radian, because this angle is in degrees. That you should be very, very clear. Right? So from tunnel test, seeing this result, you can immediately find out what is the Cm delta E. Now, once I know Cm delta E, somebody asks you, what is the corresponding value of tau? Remember, tau is d alpha t by d delta E. You know, Cm delta E can be expressed as minus Vh Cl alpha t neta t into tau. Right? Please check the formula. So you have to only use this value here. You know, if you know the tail volume ratio, if you know the Cl alpha of the tail, so you can manipulate this relationship to find out the value of tau given other things. So this is the way you can go on calculating one information based on the other information. But you have to move around this relationship only. Okay, right? Another important thing which you should know, that typically d delta E by dCl trim, what is the meaning of this? So you know that this is Cm versus Cl, right? So from one Cl I am to fly at this Cl. So this is Cl2, this is Cl1. Let's say it was delta E1, delta E2. We want to fly at Cl2, and for flying at Cl2, I need delta E2. Cl2 is the trim. For flying at trim Cl1, it was delta E1. So d delta E by dCl trim is nothing but delta E2 minus delta E1 by Cl2 minus Cl1, where these are trim values. This is important. Okay? And what is the sign of d delta E by dCl trim? Also you should know the sign of d delta E by dCl trim. You know, this is nothing but minus dCm by dCl by Cm delta E. And for a statically stable airplane, this sign is negative, this sign is negative. So total sign of d delta E by dCl trim is also negative. Right? And unit wise, you could see that it will be, this is dimensionless, this is either per degree. If it is per degree, then d delta E by dCl trim will be degree. If this is per radian, then d delta E by dCl trim will be radian. Okay? Generally, it is given in degrees. Okay? So with this understanding, I am sure you will be able to handle real life problems, including exam problems. I wish you all the best. And we are also trying to see that we give you 1 or 2 lectures on different types of aircraft, their evolution, their shapes, how the shapes have been changed, how the weight class has changed, so that you can understand whatever we have studied here, how they got translated into real product. And today you fly so many high performance aircraft, and the understanding is so simple. Okay? Thank you very much.